Good morning, students. Let us welcome to Purnachandra Higher Secondary School. Okay. So in this session, we are discussing about the second application of Gauss's law. In the previous session, we are discussing about the first application of Gauss's law, as we know, and I think you are very much clear about that one. If you have any doubt, then you can ask me in the WhatsApp. Okay. Now, in this session of video lecture, we are discussing about the electric field due to an infinite charged plane sheet. Is a very important one. In the previous session, we are discussing about the electric field due to an infinitely charged wire. That is a wire charge. Okay, charged wire, linear charge. But here we are discussing about the plane sheet. This is a very important one. Planes. So all of you look at this figure. All of you look at this figure. So this is your plane sheet having an area A. I will take it as a, look at here. This is the area A. Okay. So area A means one thing you will clear in your mind. This sheet, suppose let us take a sheet, then it is clear. Suppose this is a sheet. Sheet means this is the total area is A. That means this sheet, this surface area is also A, and also this back surface area is also A. Remember that one. Okay. So this is your surface area, charge surface area. That is your plane sheet. Okay. Which type of charge? The positively charged, as you think. You are taking a positive. You can also take negatively charged. Okay, that doesn't mean. But here I will take positively charged. Okay. So in this positively charged sheet, we are going to find out, or what is our aim? Now our aim to find out the electric field again. The electric field intensity at some point. Okay. So let us take a point P. We have just seen here. This is a point P. Okay. So look at here. For this surface, this is point P. But for this surface, I can also take a point with a similar distance. That is a very important one. With a similar distance, I will take a same point. Okay. So for this surface, I will take a point P at a distance R. And for the back surface of this sheet, okay, I will take another point P dash. Look at it, P dash at same distance R. So do not confuse kindly, students. Okay, because these planes are having two surfaces, this surface and this surface. So from this surface, because I have to find electric field intensity for this whole sheet, not for only this surface. It's a very important one. So for this surface, I will take a point P here, and for this surface, I will take a point P here. I think it is clear. Okay. So so our aim to find out the electric field intensity at this point P, and for this up surface, and from this bottom surface, I will take a point P dash here, which is also at a distance R. This is also at a distance R from this sheet, and this is also a distance R from this sheet. Okay. So now, as we have known, this is the Gauss's law of the application of Gauss's law. So that's why we require a closed surface. The sheet is not a closed surface. So what happens? Now we have to take, or we have to assume a Gaussian surface. In the previous video lecture, when we are taking a line charge. For a line charge, what type of Gaussian surface we will get? Now we will get a cylindrical Gaussian surface. Similarly, look at here. For this charge sheet, we are having a block of. This is very important. We are having a block of this Gaussian surface area. So this is your Gaussian surface. Remember, this is your Gaussian surface, okay, which is imaginary surface. Remember that one. This Gaussian surface is a imaginary surface. This is not a real one. Okay. So this is a so to calculate or to compare or to apply the Gauss law, we must assume a closed surface. So for this sheet of charged sheet, we assume what type of Gaussian surface? Now a block of. Look at it. This is a log of wood. Okay. So this is a log of wood type of Gaussian surface I will take. Okay, whose length is 2r. Remember, this is the total length from this to this. What is the length? This is r and this is r. So the total length is 2r. Remember that. The total length is 2r, and this part, this surface part area is A, and this surface part area is A. Because look at here. In this sheet of paper, this surface area is also area A, and this surface area is also A. So do not confuse. Okay. So for this surface area, I have to find out the electrical intensity at point P, and for this, the bottom surface area, I have to find out the electrical intensity at point P dash. Okay. And I think all of you very much clear from this figure. The seat, this seat, I can take this seat. This seat is symmetrical in nature. Yes or no? This seat is symmetrical. Symmetrical means this surface and this surface both are same, similar in shape. So this is symmetrical. That means whatever electrical intensity I will get for this, the same electrical intensity must I will get for this. So let us find out. Okay. So first of all, so let us again. I will go the same concept, that is for this up surface and for this down surface. First I have to find out what is phi. As you know that in the previously I have also find out the phi. So phi means the electric flux. The electric flux. Okay. So let us find out the electric flux, the up surface and the electric flux for the down surface. Okay. That means for the point P, it's simple, and for the point Ps. So phi is equal to, what is the formula? Let us take the same formula, that is integration over the closed surface E dot ds. Okay, over the whole surface area. So that implies integration, closed integration. Now here I have to split these two. Why? Remember, because again I will repeat, this set is having top surface and having bottom surface. Okay. This seat is having top surface and bottom surface. For this surface I will take P, and for this surface I will take P dash. So now, so this is E dot ds for P plus E dot ds. These are the vector quantities for P dash. Very simple. So that implies. So let us find out the one. Look at it. For this up surface, again I will take this sheet of paper. For this surface, okay, this is which type of charge? Positively charged. So positive charge with the electrical intensity direction is outward, not inward, outward. Okay. So this is the direction of electrical intensity as you have seen in this figure. And also to this area, the area vector is also in this direction. So what is the angle between E and ds? Very simple. Both are in same direction. That means the angle between them is 0 degree. Okay. So come to this side. Come to this side. This is also positively charged. That means it is also outward. Because if it is negatively charged, then it will be inward. Because I will take only positively charged, na? So that's why it is outward in nature. So outward means that this is the direction of electrical intensity, and this is the direction of ds at point P dash. So what is the angle between these two? That means the E and ds. The angle is 0 degree. Okay. So let us put it here. So integration, again close integration over P. So this is E ds cos 0 degree plus integration, close integration P dash E ds cos 0 degree. Very simple. This is also 0 degree. This is also 0 degree. So that's why. So this is E ds close integration over P plus close integration over P dash E ds. So that's why. So that's why this is integration ds. Let us take the E outside. Close integration P plus, let us take outside. So this is close integration over P dash ds. Now come to here. So this is now total flux I have to find out. So what is the integration of ds over this P surface? S. Okay, plus. And what is that surface? Again S. Very simple. S means the surface area. Surface area that is given A. So that's why in place of S I have to take the actual value E A. Because look at here. I will take what is the surface area? A, not S. So this is 2 into E. Okay. So what is the total flux through this sheet, or total lines of force passing through this infinitely charged sheet? What is the total flux? Now phi is equal to 2EA. Very simple. So let us take equation number 1. The same process I have to follow. So let us take equation number 1. And this equation is compared with again what? Gauss law. Okay. So now what is the Gauss law? So applying Gauss law, again the same process. Applying Gauss law. So what is the Gauss law? The total flux is equal to 1 by epsilon 0 times of the total charge enclosed by that cell. The same statement. Phi is equal to Q divided by epsilon 0. So in the previous video, I have taken an infinitely charged wire. That's why there is taken line charge density. But here there is not a wire. This is a surface. So that's why I cannot take line charge density. I have to take surface charge density. Okay. So what is the value of Q? Let us find out. Because charge here uniformly distributed over a surface. Remember that one. So that's why I have to find out the surface charge density. So what is the symbol of surface charge density? Now the symbol of surface charge density is sigma. Okay. So sigma is equal to the total charge Q divided by the area, that is this one. So that implies the charge Q is equal to sigma A. Remember, so I have to put this value here. Okay, so that is equal to, that is your sigma A divided by epsilon 0. Very simple. Okay, so let us take it equation number 2. I think all of you understood. Okay, where again I will repeat, where this sigma is nothing but your surface charge density. Okay, so this is the flux according to the Gauss law. The flux is equal to sigma A divided by epsilon 0. And from this derivation, from this infinitely charged plane sheet, what is the total flux I will get? 2E. So let us compare this equation 1 and equation 2. Let us compare again. Okay, so by comparing equation 1 and equation 2, so what I will get? What I will get? Okay, I would like to write here. So let us compare. So equation 1, this is 2EA must be equal to sigma A divided by epsilon 0. So by compare, look at it. By comparing this and this, I can write 2EA is equal to sigma A divided by epsilon 0. Very simple. Okay. So 2EA divided by sigma A divided by epsilon 0. Again I will write here 2EA is equal to sigma A divided by epsilon 0. Okay, so that implies what is our aim? Again I will repeat, what is our aim? Our aim to find out the electric field intensity. Okay, so electric field intensity E, so that is sigma A divided by 2 A epsilon 0. Okay, so this this A cancel out. Okay, so that implies what is the value? Sigma by 2 epsilon 0. So what is the expression? E is equal to sigma divided by 2 epsilon 0. Remember, this is very important from the problem point of view. Okay, so our aim is electric field intensity due to an infinite charge plane sheet. So I have to find out this electric field intensity, and finally I got it. That is E is equal to sigma divided by 2 epsilon 0, which is very important due to this is, remember one thing, this is the expression of electric field intensity due to this type of infinitely charged sheet. Okay, not for a line charge. For a line charge we have already derived in the previous session. For a surface charge, infinitely surface charge, the electric field intensity is equal to sigma divided by 2 epsilon 0. Now again one more thing I have to mention here. This, suppose I will take it as equation number 3. Okay, this equation number 3, what I have mentioned here, this is the magnitude. Remember, this is the magnitude value of electric field intensity. If I want to find out the direction, then look at the figure. The direction of electric field, look at this both sides, at point P and at point P dash. In the both at point P and at point P dash, the electric field intensity becomes outward, not inward. Outward. Why? Yeah, because the sheet is positively charged. Remember, if the sheet is negatively charged, then this electric field intensity becomes